Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're gonna continue the applications of differentiations. So last time we did the first and the second one. Today we're gonna continue with the third one, which is minima and maxima. So minima and maxima is just another words for minimum and maximum point, or turning point or stationary point. So recall last time that if you have a function of x or y, so we can find the stationary point by equating dy over dx equals to 0. So we can have maximum or minimum point or point of inflection. And then to find the nature of the stationary point, we can find the second derivation, second differentiation of d square y over dx squared. If the second derivation is greater than 0, then we will have a minimum point. If d square y over dx square is less than 0, we're gonna have a maximum point. But if it's equals to 0, then we have to use stable method. So with that information, we can use it and apply it into a real life example. So for example, your activity last time was to get an A4 paper. Alright, so A4 paper has a dimension of 29.7 centimeter of length times by 21 centimeter of breadth. So from this A4 paper, you need to cut a square from the corners, from the four corners. Alright, and then you're gonna have this kind of shape, and then you're gonna have to build a container. Alright, so the challenge was to cut the length of square that gives you the maximum volume. So this is our real life example. So let's say you have a factory, you want to save your materials so that you don't waste a lot of paper or a lot of plastics to create the largest container that you can build, that you can create. So let's say you have a Tupperware company, for example. Alright, so how do we know what square to cut to create the maximum volume? So most of us will resort to trial and error method. For example, the first test, we're gonna cut 1 centimeter. Then you realize that your volume is around 500. Then if you increase it, you have 800 centimeter cube. Then you increase it again, you get 1000. Increase it to 4 centimeter, you get 1128 centimeter cube. Then when you go for 5 centimeter, then you realize that the volume decreases. Then as you go on, it decreases some more. So then you realize that the bigger, it doesn't mean that the bigger square you cut, the highest volume that you can get, right? So in the end, you realize that you need to find a sweet spot, alright, so that you can get the maximum volume. So it's not as easy as cutting the largest square. So you realize that between 4 and 5, right, the highest volume decreases when you go to 5. You see that, right? So and then you explore further to 1 decimal point. As you go 4.1 to 4.2, you realize that the volume decreases again. And then you explore again between 4.1 and 4.2. Then you start from 4.01. Then you realize that the volume increases. You go for 4.02, it increases a little bit. 4.03, it increases some more. And then you go for 4.04, you increases again. Then when you go to 4.05, it decreases. You see that? 4.495, it decreases to 4.492. So the highest, the biggest length of x that you can cut is 4.04. That gives you the highest volume. So this is trial and error method, right? But this method is very complicated and very difficult to do, and it needs you to give a lot of efforts and time, and it's not even that accurate. It's only to 2 decimal point here. If you want to do more accurately. If you want to do more accurately, you have to do a lot of experimentation. So is there any way that you can you can create a formula to make this faster and easier? In fact, we have. Alright, so if we study this diagram, alright, so we know that this length is 29.7 minus 2 of this x. So we can call this 29.7 minus 2x. Similarly, this length is 21 minus 2 of this x. Alright, so this is the maths part. Okay, so if we fold it like this, we're gonna have this shape, and then you realize that the height here is x, right? So we can find the general formula of the volume. So volume, you know, is length times by breadth times by height. The length is this one, the breadth is this one, and this is the height. If you simplify it, you get this function v. Okay, so this is the function v in terms of variable x. This is just the same as all the functions that we have covered before. It's just in this case, instead of y, we use v for volume. So volume is in terms of x. Okay, so we can use this to easily find the maximum and minimum volume. Right now, some point to remember that realistically, we can only cut the square up to the half of breadth. Okay, which is 21 divided by 2 is 10.5, because if you cut more than half, if for example like these red dotted lines, then you will not be able to make the container shape. We will not be able to make this shape to create this container. Okay, so it's in between here up to here maximum. So the value of x that we can take is from 0 to 10.5. It's very important that you understand this, right? So from the functions that we derived, we can try and graph this function. So I'm using GeoGebra application to graph this function. In the end, I will have this. If you can graph it, we can easily see the maximum point and the minimum point. Alright, so from here we can see that when my x, remember that x is the length of the square, if my x is 4.04, I will get the maximum volume, which is 1128. And if my x is around 12 point something here, 12.8, I will get the least volume, which is minus 242. But this is not feasible. We reject this because volume cannot be negative. So the least volume is here, almost 0, which is when x is around 10 point something. But we only concerned about maximum because the question asks you to find the maximum volume. Alright, so we can x cannot be negative also because length cannot be negative. But graphing this function 4x cubed minus 100x squared plus 600 plus x, it's not easy. Okay, so in exam, you don't really need to sketch this if they don't ask you to. So how are we going to find this maximum point? So from our previous knowledge, we know that we can find the stationary point by finding the first differentiation and equate it to 0, right? So we can do that. So in this case, we can find dv over dx equals to 0. Okay, so to find the nature, you do the second derivative. Alright, so here is the math part that we can do without drawing the graph. So we know that stationary point is when dv over dx equals to 0. So you differentiate this and then equate to 0. So you see here we have a quadratic formula. It's not easy to solve this, so you cannot factorize this. So use quadratic formula, blah blah blah, you'll get this. So I have two stationary points. Okay, so at this point, if we don't have the graph, we don't know which one is maximum, which one is minimum. So you're gonna have to test using the second derivative. So d square v over dx square is equals to this one. So when we substitute x equals to 4.04139, you get minus 105.8, which is less than 0. So therefore this is a maximum point. So therefore x equals to 4.04139 is the maximum point. So if you do for the second point, you get 105.8 positive, more than 0, which is therefore this is a minimum point. But we don't need this, we only concerned about the maximum point. So we know that when x equals to 4.04139, you're going to have the maximum volume. So sometimes they can ask you, what is the maximum volume? So simply just substitute your x into the volume formula. So you get this maximum volume. So this is very correct from what we have seen from the graph before. So that's it. That is the application of the minima and maxima, which is very similar. It's just we're going to we just apply it to the real life situation. Now if you go back to this page on deriving the function v, this is the most important steps that you need to do. You need to know, you need to use your mathematical skills, you need to use your common sense to derive whatever functions that you need. In this case, we need the function of v in terms of x. In exam, different questions will need you to derive different types of function. Now, this is not a additional maths skill. This is a maths D skill. So all of you should be able to do this upon practice. If you don't practice, this one will be very difficult. Now, the good news is, for example, if you look at this example, they ask you to derive this function a in terms of x. But the good news is that they give you this function. So if you cannot prove this, you can just skip this and use this function to answer the next question. But you will lose few marks, okay? But try to learn this. So since you are already in Form 6, you need to know how to do this. So let's cover these examples briefly. So example 1, you have this shape, okay? So the first question is, they ask you to show the area is equals to this. In other words, they ask you to derive a equals to this function. So you're going to have to use your maths D skills to do this. The second one, given that x can vary, find the stationary value of a. To find the stationary value of a is just dA over dx equals to 0. And then you just do the maths part. So the next example is very similar also, but it's not as straightforward. So this question is talking about cuboid with surface area. So you're gonna need to know what is the formula for the surface area of the cuboid. It's better if you sketch the diagram and then you apply this dimension. So what is the length, what is the base, what's the height, then you know you can express whatever they ask you for. Part 2 and part 3 is exactly the same as example 1 and the previous example before that. So you can try this first. So this example 3 is very similar to the one that we discussed before. So you need to prove and then you find the stationary value. Okay? So with that, you can end our minima and maxima section, and the next lesson will be on the last part, which is rate of change.